Alright, this is the first section of Chapter 5. The Chapter 5 talks about thermal energy. And so we are ready to discuss the first section. Helps if I talk about the first section, which talks about temperature and heat. Alright, so the first thing we're going to discuss is what is temperature. So first of all, usually we probably discuss the word temperature to discuss something like how hot or how cold something is. So, we discuss like, hey, it's really hot outside, or hey, it's really cold outside, and so that gives us some relationship among temperature. Well, that's all fine and dandy and everything, but, scientifically, that has nothing to do with technically temperature. So, we need to talk about what is the true scientific definition of temperature. And first thing we have to talk about is that everything around us is made up of little tiny particles. Okay? So we have these little tiny particles. Particles, of course, can be atoms or molecules. Okay? Okay, and so the key is that when you have these atoms or molecules are always in motion. They're always moving no matter what. And so the faster they move, the more kinetic energy they have. And so temperature is simply a measure of that kinetic energy. So as your temperature goes up, the kinetic energy actually goes up. So like for example, when you are sick and you need to take your temperature, your thermometer is actually just measuring the number of times the particles are hitting the thermometer. So when you are sick, your particles in your mouth, for example, if you're doing an oral thermometer, are measuring when you're actually sick and you have a higher temperature, the particles in your mouth are actually moving faster, and so they're hitting the thermometer more times than if you have a normal temperature, and that's why the thermometer reads a higher value. Here in science class, we use a temperature called kelvins, and it's symbolized by the capital K. Notice that we don't use that little degree bubble, you write degrees Celsius or degree Fahrenheit. We don't use that little degree bubble with Kelvin, okay? More commonly, in your thermometers that we'll read in here, read the Celsius scale. And then we'll convert them to kelvins for a lot of our formulas. Okay, so we have this stuff called thermal energy. Thermal energy is just the sum of the kinetic and the potential energy of the particles. So we had in the last chapter, if you take kinetic energy and potential energy and add them together, you get mechanical energy. Well, this is more specific. This is of the particular particles of something. So if you have, atoms, kinetic energy, atoms, potential energy, you get thermal energy. So, if the temperature increases, the kinetic energy increases. Therefore, then what happens is that the thermal energy should still basically remain constant because the potential energy would therefore decrease. Alright, we have this stuff called heat. You guys are used to heat. We're getting close to where we're going to need some heat. It's basically where we have thermal energy that flows from an area of higher temperature to an area of lower temperature. So your heater at home, it puts off heat, and then it goes to areas where it is cold. It's a form of energy. We measure it, therefore, in joules. Heat always flows from warmer to cooler materials. Okay, so now we have this thing called specific heat. Alright? Specific heat. Every single object has a certain amount of heat that something will absorb. It'll only take up so much heat. And that temperature change depends on the substance that you have. So, basically specific heat is the amount of heat that's needed to raise the temperature of 1 kilogram of some material by 1 degree Celsius. That's an object-specific heat. And every object has a different specific heat. The specific heat of an object is measured in joules per kilogram times degrees Celsius, or we can replace that with Kelvin, either one. Water is an example of a coolant. It has one of the highest specific heat values. It can absorb a lot of thermal energy before it breaks down. So if you notice, I even put a chart over here. So look, water has a specific heat of 4,184 joules per kilogram times degrees Celsius, whereas something like iron only has 450. The reason the water has such a high specific heat is because it has very tight, strong bonds. It makes these really strong intermolecular forces that causes it so that it can absorb heat before it breaks apart. So, because water is very useful, or has those strong bonds and can take in a lot of energy, it's very useful as a coolant. And basically a coolant is just a substance that's able to absorb a lot of heat. And so compared to other materials, the temperature of water will increase a lot less when it takes in that heat. We are able to calculate how much energy an object changes when we take in heat by using a thermal energy equation. So here's this equation. Q equals S times M times delta T. Now, it looks a little intimidating, but we can talk about like what each part of this is. Q just stands for thermal energy. And again, it's an energy value, so what do we always measure energy in? It's going to be measured in joules. We have the specific heat value. This one's going to be in joules per kilogram times degrees Celsius, or you can replace this value here with Kelvin. You have M, which is mass, okay, which is in kilograms, and then you have delta T, which stands for, anytime you see a delta, it just means change. I think we talked about this a little earlier with something else. It just means change, which means a difference in temperature. So that means that I'm going to take the final temperature minus the initial temp. Oops. Okay. And those temperatures can be degrees Celsius or Kelvin. It does not matter. Okay. So there's each part of the equation. You can watch the changes in thermal energy video to do some practice problems. I'm not going to do it here on this video, so it's not so long. So if you want to just click on that changes in thermal energy video, you can watch some examples. Alright, so a couple of the things about energy. There are two types of energy that we haven't talked about, or two words that explain energy. When energy is given off by a system, we call that exothermic. I remember this one because it has the word exo in it, and so that reminds me of the word exit. So it's exiting the system, it's going out. If you have an exothermic reaction or something that is exothermic, it makes things feel hot. So I think of those like little heat packs that you like crack and they make your hands nice and warm in the winter. That's an exothermic reaction. The chemicals come together, there's so much energy being given off by the reaction that it makes it feel warm. You don't actually give off cold. A reaction where energy is taken in, it requires energy to go, so we call that endothermic. You have to take energy in. So that actually gives you the sensation that it's being cold because all the energy in the environment is being pulled in. Alright, Now, we can measure specific heats of different things or measure thermal energy of different things using a device called a calorimeter. It's just a fancy little device. In fact, it doesn't even need to be fancy. We can use them in class and make them out of styrofoam cups. Basically, it's just a chamber within a chamber. You need to have something that basically has an outside for, and then you have an inner chamber usually. If you use styrofoam, sometimes that's thick enough where you don't have to have an inner chamber. Obviously, the nicer ones, they have two. They have an outside chamber and an inner chamber. A cover, something to stir, usually thermometer. But the general gist of a calorimeter is that you take some heated sample and it transfers the heat to water so that you know all the heat's going to an amount of water, which water we know all the information for. So we are able to figure out basically that water's, or that unknown metal's thermal energy and figure out what it is by using this device. So, and we'll get in a lab and we'll do some different things with this so you'll understand a little better, but I wanted to give you an idea of what a calorimeter looks like and what a real calorimeter looks like, because we'll probably make ours out of styrofoam cups and such. So, that's the end of this video. Like I said, make sure you check in on the thermal energy calculations so you know how to do those.